This video will focus on the analysis component of the IB internal assessment. And as part of the analysis component, we are going to discuss the rubric that's used to assess student work, raw data collection, which includes both qualitative and quantitative observations, and then we'll transition into sample calculations, graphical analysis, and how students are scored in relation to the assessment rubric. Throughout this internal assessment analysis video, there are specific learning goals that students should be able to achieve by the end of them watching this. First of all, they should be able to fully understand the expectations of the analysis. In other words, it should not be ambiguous what their expectations are, and they should be able to understand and explain what the expectations are. Similarly, they should be able to correctly record qualitative and quantitative data. And what this means is that they should be able to generate tables and graphs effectively without any issues pertaining to titles and decimal place consistency between recorded values and uncertainties. They should also be able to propagate error and showcase thorough sample calculations so that any teacher or any reader of the report should be able to understand what exactly they're discussing. Students are also expected to be able to conduct thorough graphical analysis in terms of trends and error. Error pertains to both systematic and random error, and the trend is associating with whether or not the relationship between experimental variables is linear, quadratic, and also is there a positive, negative, or no correlation between variables as well. Students, because of this video, should also be able to self-assess their own level of performance if they're skill building and working their way up to generating an analysis section of an internal assessment. These are the learning goals for this video. This is an adapted version of the IB analysis rubric for their internal assessment. And as you can see, that the scoring system is designed from 0 all the way up to 5 to 6, with 6 being the top score that's available for this component. There are 4 sort of subsections of this analysis component: qualitative and quantitative data, data processing, measurement and uncertainty, and interpretation of data. Each of these is worth anywhere from 0 to 5 or 6. And ultimately, what the teacher is supposed to do is assign a score for each of these criteria. So what happens is, for instance, if your lab is marked 5 to 6 for your data collection, then only a 3 or 4 for your data processing, and then again 3 to a 4 for your measurement and uncertainty, and then you jump back up to a 5 to a 6 for interpretation of data. What the teacher does is they look at all of these different components of scoring and they assign you a mark out of 6. In this case, if you got 5 to a 6 here, and then a 3 to a 4, a 3 to a 4, and then back up to a 5 to a 6, your score would be most likely either a 4 or 5, depending on how positive the teacher interprets your level of work. So just to summarize, the analysis components out of a total of 6 marks. Each of the 4 criteria are assigned a score, and then the teacher assigned you an overall score based on sort of the weighted average or the quality of your overall work for this particular component. As you can see right here, this is an example of an actual previous IA from a student. And what I've done is I've added these boxes to highlight some of the descriptors that a teacher or an IB moderator might say particularly about this sample of student work. So when you're creating qualitative observations, there's a couple things that you should be sort of cognizant of. First of all, do you have a descriptive title? In this particular case, the student writes raw, qualitative, quantitative data. However, we have really no idea what kind of chemical process has been occurring in this case. So as you can see, the descriptor box here, more descriptive titles should have been included for the observation section. When you're making a title for a lab report, you always have to make sure that you're very thorough and very detailed so it's not ambiguous what's included in your table. Secondly, the student has done a very good job of separating qualitative observations into 3 different sections. During second component, and then after. So by creating these 3 stages of observation reporting, we can actually track sort of the process through to see what occurs at the end versus the start. This is a good idea opposed to just simply stating how we perform the observations that occur, because we actually develop a timeline by creating these 3 different columns. So just to review, the first thing that you want to create is you want to make sure that you have a descriptive enough title to represent your qualitative observation section. Secondly, by trying to organize your observation table before, during, and after, it allows us to sort of understand what's occurring over the duration of time, opposed to a random list of point form notes about observations that were taken. The more detailed your qualitative observations are for your internal assessment, the better, but you just don't want to be too redundant whereby you're taking a full page by not being quite as precise. When you're designing your raw data tables for an IB internal assessment, there's a couple things that you should be focusing on to make sure that you don't get a mark reduction. The first of which, similar to qualitative observations, is creating a descriptive title that allows the reader to get a clear idea of what you're representing in the table below. So this candidate did a good job by, first of all, numbering the table, raw data table number 1, and provides enough detail for us to understand what he is discussing below. The second thing that you should be thinking about when you're recording quantitative data is whether or not you're including your uncertainties, include all of the relevant raw data to maximize your chance of getting a 6 for this component. And then includes a decimal place that is precise to 0.01 moles per deciliter cubed. In this case, we know how precise the instrument that was used to measure the concentration, or to measure the volume, or to measure the mass. Whatever the unit is technically irrelevant right now. What is important is that you understand whether it's an analog or a digital scale, and you record with consistency. This is also shown over here in terms of kPa, the pressure measurement. The student has recorded the absolute uncertainty to 2 decimal places, and this is consistent in the table below. 2 decimal places and 2 decimal places. Anytime you're recording raw data, it's essential that you have consistency between the precision of the instrument that you used, which is reflected in the uncertainty recorded, and the raw values that are also recorded within your table. As we look at the second raw data table of the student's work, we can again analyze it to see if any mistakes have been made. First of all, we can see again that we have 0.01 kPa as our pressure uncertainty, and we can look vertically down to see that all of our decimal places are also quoted to a consistent number of significant figures. This is also true with the thickness of flask glass and also with the circumference recorded here as well. However, one thing that students often forget in the quantitative component of an internal assessment is including all of the raw data measurements. In this particular case, there were some volume and mass measurements that were still missing. So because of this, that risks or makes the student more susceptible to getting a 4 or 5 for this component, because even though the data has been recorded correctly, technically the student hasn't recorded all of the raw data that was completed during the lab review. Therefore, as a reminder, always remember to include your uncertainties, consistency, but also to include all of the relevant raw data to maximize your chance of getting a 6 for this component. The data processing section of a successful internal assessment consists of 2 major components: sample calculations and uncertainty propagation. The whole point of including sample calculations such as this is that it allows the reader and the IB moderators to clearly understand the mathematical processes that were used in your lab to come up with your final answer in an attempt to answer your research question. Therefore, it's a good idea to use clear word equations before each sample calculation, which is very clear, as you can see here by the yellow highlight. Another thing that you should always try to remember is that you don't want to be redundant with your sample calculations. And what this means is that you only need to show one type of calculation in your lab. In other words, you don't have to repeat the same calculation to show how you've done it more than once. In this case, the student has clearly identified trial 1 and has subtracted once to determine the vapor pressure, and then below, all they've done is they've averaged the other 3 values. So you can see that 8.28 was calculated once, but the student has not shown where 7.75 or 7.81 has been derived from. And this is because we assume that he has followed the same process as shown by trial number 1. Furthermore, it's important that students include units for every step. The IB internal assessment is your final representation of your lab skills, and therefore you should be clearly showing units throughout. In some labs or some internal assessments, averaging is very relevant if you don't do a scatter plot. And what this is used to is it's used to reduce the amount of random error between your respective trials in an investigation. Therefore, it's always important that you show your average, you show all of your equations, but not only that, you also show your uncertainty propagation as well. This is the responsibility of every internal assessment writer to clearly show error propagation through to their final answer. And what that means is taking the uncertainties that were recorded in the raw data tables and transferring them through to the final answer. As you can see in this case, although the math is not overly sophisticated, the candidate has clearly shown their error propagation, and they propagated it through to units and then converted it to a total percent uncertainty. In addition to this, the student has gone the extra mile and has included personal justification as to why those uncertainties were propagated the way that they were. As you can see, he has written, as difference between the circumference and thickness was calculated, absolute uncertainties of the two must be added. As the value was subsequently squared, uncertainty would be doubled. The point of the matter is that students have to make an effort to propagate uncertainty throughout their entire lab report, and by getting and putting in these personal points of justification, it's technically increasing the odds that students can reach the 5 to 6 in the rubric opposed to scorers only reaching 3 or 4. After the sample calculations have been shown and the error propagation has been thoroughly explained, a good IB candidate presents their process data and summarizes it in a clear table. In this particular case, the candidate has done a good job of labeling and calling it table number 1 with a descriptive title, and they also have retained consistency in terms of the uncertainty they've used and what they've recorded below. This is true not only for concentration, but also for the percent uncertainties and their total vapor pressure. As you can see here, we have 4.1 and also 3.4, both of which are quoted to the same number of significant figures and to the precision of 1 decimal place. So they're quite consistent. You can't notice anything here. Also, in the highlighted area, we've got 7.09 and 7.95, both of which have a total of 3 significant figures and 2 decimal places. Okay? This is in line with the original uncertainty that was used for pressure recordings. So just to summarize, regardless of the type of calculations that you complete in an internal assessment, it is your responsibility to make sure that you summarize that data in a very efficient and effective manner. And what this usually means is by creating a process data table that's clearly described, that consists of correct table formatting with consistency between values and also between uncertainties in terms of the instruments that were used. One of the most important aspects of the analysis component of an internal assessment is the graphical analysis section. In this particular case, the student does a good job of including a descriptive title that can make it very easy for the reader to understand what is being shown below. However, the student has made a small error by not including a number to be associated with this graph. In other words, they could have included graph number 1 and then included the title, or graph 1.1. This kind of numbering system makes the conclusion section more concise as links are made from the graph to the experimental variables. Because a number is not included, the candidate will now have to include more of the title in the conclusion and evaluation section, which will add to the page limit and also make the paper less concise than it could be. This will be reflected in their communication score for their internal assessment. Generating a clear descriptive title with a numbering system is not the only thing that students have to do if they wish to be successful on their graphical analysis section of an internal assessment. What they should also be cognizant of are including clear labels associated with their graph. As you can see here, the student has clearly labeled the x-axis as concentration of ethyl ethanoate solution in moles per decimeter cubed, and relevant units are included and very clear. On the y-axis, we have vapor pressure of ethyl ethanoate solution, and also our KPA representing the pressure unit that was used to record the values. Aside from that, the student has done a very good job of including relevant error bars to show the degree of deviance amongst values that he or she used to calculate the average. The average is depicted or represented by the data point shown. You will also notice that the student has included 2 different types of error bars, both vertical and horizontal. The vertical error bar is showing the deviance in terms of the vapor pressure that was calculated in this investigation. However, when we look at a horizontal direction, the horizontal error bar is representing the error associated with the concentration of ethyl ethanoate solution. By including this, we can see more of how much those average data points that are represented by this 1 here varied both in the vertical and horizontal directions, which can give us a bit more insight about what is not shown in the graph. The average values are plotted, but by showing this vertical and horizontal error bar, it gives us a bit more understanding about whether or not there were any outliers that were taken in and created in this average. In other words, they might have been hidden. The student does an excellent job of also showcasing the correlation coefficient and the root mean square value for this correlation. Because the correlation is above 0.95, we can assume and make these and conclude that there is a strong positive correlation between the concentration of ethyl ethanoate and the corresponding vapor pressure that is measured in this investigation. The root mean square value also can show whether or not there's a lot of deviance from the trend line. In this case, this is a strong positive correlation, and the student has done a good job of representing this by showcasing those values. There can be greater analysis done to this in terms of calculating the slope and looking at alternative things, but that, of course, will depend on the nature of the internal assessment and the type of calculations that were done. Students may also choose to show a complete scatter plot and not average their values if they feel like the distribution is best represented that way. That, of course, depends, again, on the type of data and the goals of the student's internal assessment in the first place. So to summarize, a student must include a clear descriptive title with clear numbering or a clear number system. They must have clear labels, and they must show error bars to represent deviance in the propagated values. By including correlation and root mean square values, this gives the moderator a better idea of how strong the relationship is between the variables. And this is something that students should always try to do, especially when they're creating a trend line to analyze their data in internal assessment. After the basic components of graphical analysis have been completed, many students forget about the benefit of creating error bars when it comes to linking their graph to their conclusion and evaluation section. When we look at this here, we can see the deviance in our dependent variable and also the deviance horizontally in our independent variable. Now, because the student has created the trend line and they've also shown vertical error bars, what this allows us to do is to analyze the level of systematic error in this investigation. Systematic error is caused by variable control or the lack thereof, or in terms of general flaws in the experimental design, such as no calibration and improper filtering techniques, for instance. In this particular case, because the random error is represented in vertical lines, okay, is the deviance between data points, or the reliability, in other words, we can assume that systematic error in this experiment is quite small because the line of best fit falls within all of the vertical error bars in this direction. So if, for instance, I drew another line that was way up here or way down here and outside of these error bars, we would assume that there would be a significant amount of systematic error present in the investigation that was causing the value calculated to be true below the true value. However, in this case, the line does indeed follow and fall between the vertical error bars, which suggests that systematic error is quite small and random error is contributing to this experiment in terms of why there's a deviation from the true value. So to summarize, error bars are not only there to show us deviance, but they can also help us to measure the level of systematic error by looking at whether or not the trend line falls within their vertical error bar range. This can be beneficial when students try to connect and explain their results and why some errors caused a deviation from the expected value. Since only one example internal assessment was used for this video, it is possible for us to easily summarize the final score for the analysis component. In terms of A1, qualitative and quantitative data, the student did a very good job of recording the data in tables correctly and also included relevant qualitative observations. However, the mark band of 3 to 4 is more representative of this student's work for this component because of the fact that they didn't include a descriptive title for their qualitative observation, and also they forgot to include some volumes and mass values that were not directly used in calculations for this lab, but should have been still discussed in the evaluation conclusion because they also contributed a specific amount of random error. That gives this component probably a 4 as being the most accurate representation of this student's work. In terms of data processing, the student did a very good job of including very clear and descriptive sample calculations that included word equations, error propagation, and even justification for the error propagation technique that was used. Therefore, the score for this regard, A2, is best represented as not a 5, but rather a 6. For A3, measurement and uncertainty, the student also did an excellent job of showing the consideration of uncertainty, not only in the tables presented, but also in the error bars that were shown. Therefore, the student recorded the correct uncertainties in tables, propagated the uncertainty, and also included error bars in the graphical analysis, which also give an overview to the moderator that the student is cognizant of the level of random error throughout the entire report and not just in terms of recording it at the beginning. For this component, the student has scored also in the 5 to 6 mark band, with a 6 probably being the best representation of the results. Leaving our last component, A4, interpretation of data, and it reads, the data processed or the processed data is correctly interpreted so that a completely valid and detailed conclusion to the research question can be deduced. Well, in terms of the data collection, a sufficient number of trials were indeed included, and the data was indeed included in the raw data table. It was processed, and then it was represented in the form of a graph with the correct linear trend line, and also the correlation coefficient and the root mean square values included. Since the error bars were included, the student can also analyze the level of random versus systematic error that indeed can support the conclusion that they form, or can denounce the conclusion if the level of error was beyond a legitimate level. Therefore, there is no reason why this candidate should not get a 6 out of 6 for the interpretation of data, assuming that their conclusion and evaluation supports and is in line with what they graph. The next step comes to the moderator assessing all of these different criteria and coming out with a final score. Since most of them are in the 5 to 6 mark band, and only one is in the 3 to the 4 mark band, it is assumed that 5 to 6 is probably a more correct representation of this student's work for this component. However, because the student forgot descriptive title and also was a bit suspect in terms of including dilution data associated with the volumes and a few tiny mass measurements, the overall score for this criteria is best represented as a 5 out of 6. A 6 out of 6 is not obtainable because These dilution values and mass values here that were excluded are relevant to the conclusion and the interpretation of data that would occur subsequently in this investigation. Therefore, I'm confident to state that this is a 5 out of 6 student exemplar for the analysis component of this internal assessment.